will be explaining the difference between batch gradient, stochastic gradient, and mini-batch gradient. So these algorithms are used in optimization of functions, and we often need these optimization functions because at the end of the day, when we want to build a machine learning model, um, let's say linear regression, or any other um, model that we want to build, we have to mathematically describe it. We have to turn it into a function. For example, in case of linear regression, we optimize the function that's basically the errors. So, for example, let's say we have a function of error, and when we find the minimum point of this function, it means that the variables that we find will give us the minimum error. And I will explain all of them with an example. The simplest form of gradient algorithm is batch gradient. It works with small data sets well. It is stable, but the problem of this batch gradient is that it is computationally expensive, and I will tell you why. Let's say we have a data set and we have points. I'll go with a very simple example. Let's say we have a data set that contains area and price, and we have areas like, let's say, x1, x2, x3, x4, and we have price y1, y2, y3, y4. And we want to build a linear regression model given the area that will predict the price. And basically this is this is the plot of this data set. So in the x-axis it's our area, and in the y-axis it's our price. So we need to find a line that fits the best into this data. And once we find that line, for example, let's say it's this line, it means that by using this line we can predict price. But how do we do it? Let's say we draw a random line. We drew a random line, and then we calculate the distance between the data point and the line. And let's say it's like D1, D2, D3, D4, D5, D6. D3, D4, D5, D6. We can write it as M is basically the number of data points in our data, Di. And what is this Di exactly? And as you can see, we started with a random line. And this random line has, of course, it has parameters. From geometry, you probably know when we describe a line, we have two parameters. This is v1, x plus b. B is the y-intercept, and y is the slope. So in our case, by drawing a line, it basically means that we started with a random parameters. And let's say this random parameter was t1, t1, and this random parameter was t2. Right, so we did this. And then how do we calculate it? How do we calculate this distance? Again, we'll write the same thing, but with a little more details. We add, what is the distance? Distance is basically this point. This point is basically the real price, which is y, area, and x. And what is this? This point is the point that is generated by our random line. So this means that this point can be mathematically described by the point that by the line that goes through that point. And we write it as, so it means that if with our random line, if we were to predict this price, it would actually give us this value with these parameters. And we write it as y minus y hat m. Y is our prediction. No, y is the real price, and y hat is our prediction, which is basically this distance here, d1. And let's denote this prediction with these parameters, which was, let's say, y, w. I'm not sure if I was calling this y before, but it's actually w. I'm sorry. So y multiplied by x1, our input, plus b minus y. And we're going to take its square because we are interested in the distance. It doesn't matter whether it's minus or plus, that's why we're going to take its square. And this is basically the loss function. So then how do we use batch gradient to proceed with our algorithm and to go towards the optimum? So we had these parameters, and we update these. In our case, this is constant. This is a constant. So our function is basically it's dependent on W and B. And so what happened here is that this is our loss function, right? And we can draw our loss function here. So the input of this loss function is B and W, and the value of the loss function is here. And let's say this follows this curve, this function. And we need to find the value of W and B that will give us the minimum Y, because our loss function, the sum of errors should be minimum. So as you can see, it's this point. And you remember we started with a random W and B values. And let's say that those parameters W and B corresponds to this point. So, and then we try to find a way to go from this point to this point, and we can do it iteratively actually. So we started with this, we came to this point, and at this point, if we calculate the gradient of this loss function, it will show us the direction to the minimum. I won't go into the details of why it gives us a direction towards the minimum. I have another playlist in YouTube you can go and check, but it gives us the direction towards the minimum. And the calculating the gradient of loss function, it means that we take the derivative of this loss function with respect to W and B. And we can take it. And what does it mean is that we take the derivative of this loss function, and then what we should do, we have to move in this direction, right? And how do we move in this direction? We update our parameters. It means that our parameters will go in this direction. So let's say it will be somewhere like this. And how do we get to this point from here is that we basically update them like this. Oh, sometimes it doesn't work. Okay. So this is the new updated parameter, so we can denote them as vi, bi, plus 1 is equal to vi, bi, bi. So we do it for some number of iterations, and that number of iterations is actually a hyperparameter. And we also can choose how fast we go in the direction of optimum value. For example, if we choose a number of iterations too long, let's say 2000 times, then the steps we take will be more, and we that's not, maybe it will work, but the point is the number of iterations. The steps will be smaller to reach the minimum. On the other hand, if we oh, actually, no, what I said is wrong. If we, as we increase the how much we, how many steps we take to reach the optimum is actually dependent on uh, the rate that we choose. For example, if we choose the rate bigger than what is optimal, then it will, for example, from this point, it will go like this, and then from this point, it will go like this. So you can basically miss, um, you can basically miss the minimum. So this is not what we want. And also, if we make it smaller than what is optimum for this hyperparameter, then it will take a lot of steps to reach. Let's say, so each time what we are doing, um, we are updating the parameters, then we calculate the new loss function, and then from that point we go again, we do it again. Okay, if it's so small, it will take more steps. So we need to find a good balance between we don't want to miss the minimum, and we also don't want to take very small steps, because then it will take a very long time for our function to converge. So we can try different parameters, different rates to find the optimum one. And we can define that rate as L or lambda. And what is the downside of this gradient function? The downside of this gradient function is that in each step, when we calculate the loss function, we use all of the training samples. We use all of the training samples. So that's why I said gradient descent is not bad for small data sets because the training samples are not that long, are not many. But if our training set has, let's say, 2-3 million training samples, then it means that in each step we are going to use we're in each step we are going to use that 3 million training samples in our gradient, which is not very good. That's why they came up with stochastic gradient descent. Stochastic gradient descent. It's very similar to gradient descent, but instead when we calculate the loss function, we don't do it for we don't do it for all of the training samples. Instead, we choose a random training sample and then we calculate its gradient. So instead of this, I will copy it. Okay. Instead of this, we get rid of the sum. And this xi, our training sample, is randomly chosen. So we can write it as I our random function that returns a value between in the range of our training set. So let's say 0 and length 0 and m, right? So then it becomes y. Yes. And we calculate the loss function. We calculate the derivative of this, and with gradient of this. Then everything is the same. We just change this part. We just change this part. So the advantage of stochastic gradient descent is that instead of using all training samples in every iteration, we just use one training sample, randomly choosing one training sample. It's very important that this method of choosing should be random. So instead of we just, as I said before, we just choose one random training sample in our loss function. And lastly, what is batch, mini-batch? Mini-batch is something in between stochastic gradient descent and gradient descent. Stochastic gradient descent and batch gradient descent. So we had this sum here. Let's go back to, I actually shouldn't have deleted. So instead, let's say x1 plus v. So instead of, for example, in each epoch, in each iteration, instead of calculating for a randomly chosen training sample, we don't do that, and we neither calculate, neither do we calculate all trainings, neither we include all training samples in our loss function. So instead, let's say we have m number of samples in our training set, and let's say it's 120, and let's say our batch size is 40. So we have a for loop. We have a for loop that runs 3 times, and then we have in that 3 time we have 40 40 times, and then plus b. So we can also write bi here. Not bi, sorry. B is just a parameter. And we update we update update it like this. So that's basically what it is.